All right, so getting into the binomial theorem now, so lesson 29. First off, I kind of want to go through like where we're going with this, like why we're even going to be doing this. Do you remember in the last unit there where we found ways to factor large polynomials? So if we had something like, x to the 4 plus 3x to the 3 plus 2x squared plus 5x plus 4, right? Do you remember how we figured out ways to factor these larger polynomials? Well, because this would be a pain in the butt to try to do it by guess and check or anything like that, right? We got a similar problem just on the other, like the other way now, right? Is if we had something like this, right? Let's say that we had a situation like 3x plus 4y to the power of 7, right? And we were told to expand that. Well, we could do that, but it's going to suck because we're going to have to go 3x plus 4y times 3x plus 4y times, and you see where I'm going here, right? We'd have to expand everything. We're going to end up with just a ton of terms here, and then we're going to have to collect all those like terms. This is way too messy, right? So this is where the binomial theorem comes in. We're going to find, well, a pattern in this, right? That's kind of what we're doing first. And then we're going to be able to make like an equation, a general equation out of that. And then use that to figure out any individual term in the expansion of something like this, right? So here, let's look closer at this now, see what's going on. So if we look at just x to the y to the power of 0, then that would just be equal to 1, right? Because anything to the power of 0 is just 1. But we can also see that we've got the number of terms in this case is going to be 1. So like terms is 1. The exponent is 0. And the row that it's in is 0. Okay? Now, we're going to be using these three things a lot through this lesson. The number of terms that this has, the exponent, and the row that it's in, like 1, 2, 3, like the row that's in there. So I'm going to be referring to that a lot. So now, in the second one, I'm going to shorten this. This will be the number of terms is 1, 2. Yeah, T is a bad example. I'll write terms. Okay, the terms is 2. The exponent is 1. And the row that it's in is 2. Okay, and the next one, I'll just do one more. So the terms is 3, right? There's 3 terms there. The exponent is 2. And the row that it's in is 3. You guys kind of see the pattern happening here? Oh, sorry, not on that top one. That should have been row 1. Sorry. Now we have a pattern. So the terms and the row match each other, right? Terms and the row will always match. The number of terms that we have and the row that you're in will always match, right? And the exponent is always 1 less. The exponent is always 1 less than the number of terms that we have going on. Okay, so that's our first part of our equation that we're going to be making here in a bit, right? So we're just finding patterns to begin with. So here's properties of the expansion of that. So there are n plus 1 terms. Okay, so if your exponent is 3, then that means there's 4 terms, right? So 3 is like my n value. The sum of the exponent of x and y in each term is equal to n. So if I look at in any individual term, right, this is x to the 2 times y to the 1. 2 and 1 gives me that 3, right? And that's going to be the case for any of them, right? 2 and 2 gives me the 4. 3 and 2 gives me the 5. So that's all that's saying. The other pattern we're seeing here is that the exponents of x decrease term by term from n to 0. And what that means is that if we look at this one, like it starts at 4, right? Then it's going to start at x to the 4, x to the 3, x to the 2, x to the 1, and then there's no x. And the y's do the opposite. You can think about this as being like y to the 0, right? So the pattern is there. So it's like y to the 0, y, and then the y. So the y's count up. So the x counts down, and the y's count up. Okay, that's pretty much, the next part. And then the coefficients in each expansion, they form a symmetrical arrangement. So we're going to get into that'll be the next part of this, is figuring out what is this arrangement. But can you see that we've got, like, 2 and then 1 and 1? And this side we've got 1, 3, 3, and 2, and 1, and then 1, 4, 6, 4, 1. Right? You guys see the pattern happening there? And then as we go down, we're going to figure out how we actually get those numbers for the coefficients there. Okay, so how many terms are there in the expansion of 2x plus 3? Okay, so we know if this is like my n value, then the number of terms would just be 8 plus 1. So there would be 9 terms in this. All right, if there are 18 terms in the expansion of this, then what is the value of n? Okay, so if there's 18 terms, right? 18 terms, then my n value would be, here, let's just write it out again, 3x plus 2y to the power of, if there's 18 terms, I know this must be 17, right? Your n value is always 1 less than the number of terms. Okay, so if that's true, then I can say, okay, if that's actually equal to 17, and that's also equal to 2n plus 5, we can say, therefore, 17 is equal to 2n plus 5, and then just solve for n here, right? So then we get 12 is equal to 2n, and then n is equal to 6. All right, Pascal's triangle. So getting in now to, like I said, those coefficients, like what's actually happening here. Well, the coefficients in the expansion of just the general x plus y to the power of n can be put into a triangular array known as Pascal's triangle. Okay, so the way this works is we'd have 1 at the top. Okay, I just want to show you first how this is the same thing, right? Here's Pascal's triangle, and then there's the triangle we were dealing with. And if we just look at the coefficients, right, so 1, and then here we've got 1 and 1, and then 1, 2, and 1. Well, that's the same pattern we got going on here, right? So same thing there. Now, what is happening here? Well, the pattern I'm starting to see, right, is that if we took this one, right, plus this one, and like added them, we get 2, right? And that same little pattern kind of happens everywhere. 1 plus 2 is 3. 2 plus 1 is 3, right? And even if I jump down here, that's the same thing. 4 and 6 give me 10. Yeah? So you guys kind of see like the pattern that's starting to emerge there? So if that's the case, it says now use the pattern to make the next 3 rows of Pascal's triangle. So that won't be too bad. Let's say, okay, that'll be 1. Actually, that'll be 1 and 1. We can make all those right off the bat. All right, and then carrying the pattern down for the next spot here, right? That's just going to be 1 plus 5, so this has to be 6. Okay, and yeah, we can just kind of go from there. So 5 and 10 is 15. 10 and 10, 20. 10 and 5, 15. And when you get half of it done, the other half's easy, right? That's going to be like that, and then there was a 1 on the end as well. For the next row there, we're going to have 1 and 6 would be 7 in that spot. And then 21, 35, and then 35 again, and then 21, 7, and 1. And then the last one's going to be 8 in that spot, 28, 56, 70, and then 56, 28, 8, and 1. Okay. So now it says using this, it says use Pascal's triangle above to expand the following binomials. All right. Okay, so let's think about this for a second. So if it's going to be x plus y to the power of 6, well, one thing I know about this when I expand it all out is that there's going to be 7 terms, right? I'm in the 7th row, and there's going to be 1, 2, 3, 4, 5, 6, 7 terms, okay? And yeah, and we'd also be in the 7th row, right? So if this is my first row, so 1, actually that's confusing, isn't it? 1, 2, 3, 4, 5, 6, 7. So I'm looking at this one. right? That's going to be our info here. Okay, and then the other part, I guess, is that let's do our x's first, like just the x's. Well, x's and y's, I guess. We'll say, okay, well, this first one I know is going to be something x to the 6. And it'll just be x to the 6. If you really want to, you could write y to the 0, but I'll leave it like that. The next one's going to be x to the 5, y to the 1. Next one would be x to the 4, y2, x5, y3. Whoop, that's not right. I gotta count down. Okay, that's gonna be 3, and then y would be 3. And then x would be 2, y would be 4, and then x would be 1, y would be 5, and then the last one would just be y to the 6, right? So there's what's going on with my x's and y's. Now I can really just use Pascal's triangle to figure out my coefficients, right? So adding all those, now I can see that it's really just going to be, well, 1 to begin with, and then 6, 15, 20, 15, 6, and 1. And then really, remember, these were all being added together too, right? We should have had plus sign symbols. Plus, 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 and plus. There. No big deal, right? Now, this is kind of annoying though, right? To actually do it with, drawing out Pascal's triangle every time. So we've actually got another method. I'm going to skip this one just for the sake of time. It'll be the same thing, right? But we would just end up using the last row instead. Okay, so one of the most useful things about Pascal's triangle is the connection between the triangles and combinations. So that's how this fits with the other lessons in this unit, right? Is that our general equation in the end is going to have combinations in it. Okay, so as it turns out, the entire triangle can be written like this instead, right? So you can see 0C0. Well, that's just 1. 1C0, well, that's 1. And 1C1, that's 1. 2C0 is 1. 2C2 is 1. And then 2C1, right? That's not, now that's actually 2. Okay, so that's that one. And this pattern continues all the way down. Again, just to kind of remind ourselves about the rows here, let's write them out. So that was row 1, 2, 3, 4, 5, 6, and 7. The exponent for that, when we were expanding out x plus y to the power of n, so the exponent, n, would be 0 for the first one, and then 1, 2, 3, 4, 5, 6. And then the number of terms was the same as the row number. Okay, so that was 1, 2, 3, 4, 5, 6, and 7. Okay. And that's what they wanted us to do there, okay? So, and then we're kind of getting there. We're putting everything together, and then we're going to make one equation out of this thing. So another pattern is that the sum, if, well, let's write this down again. So if we had row number 1, 2, 3, 4, 5, and 6, the sum of the coefficients, right? So if I add up all of the coefficients, like add up everything in this line, and add up everything in this line and everything in this line, right? This follows a pattern too. So let's kind of figure that out. I'll kind of show you when we do this. So the number of terms in this one, so row number, that is the same, right? So now 1, 2, 3, 4, 5, and 6. And the value of n again, so this is like our exponent, would be now 0, 1, 2, 3, 4, and 5. Now it turns out that the sum of the coefficients for the first one would be, for the first row, would be 1, and then 2, and then 4, and then 8, and then 16, and then 32. You guys might be kind of seeing the pattern here, right? That this comes, we can get these same things by going 2 to the power of the row number. Sorry, not the row number, 2 to the power of the exponent, right? So 2 to the power of 0 in the first one would be equal to 1. 2 to the power of 1 would be equal to 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. And 2 to the power of 5 is 32. Okay, so that's just a nice, like another nifty little thing there. So, okay, let's use that. So it says now, what is the sum of the numbers in the 12th row of Pascal's triangle? Okay, so if we're talking about the 12th row, then do you remember how that would mean that our n value or our exponent would be equal to 1 less? So our exponent here is 11. So then I don't need to like figure them all out and add them all up. We can just look at this pattern and say, okay, well then adding them all up would end up giving us 2 to the power of 11, which is equal to 2048. Okay, and then this one's actually even easier. What's the sum of the coefficients in the expansion of this? Well, okay, well that's just going to be 2 to the power of 9, right? 2 to the power of the exponent. And then whatever that is, we'll leave it like that. Okay, what is the sum of, and then they've got it written out with combinations instead. Okay, so if we think about this, right? This was our first one, and it goes all the way up to 10. This is actually going to be like our exponent value of 10. If you wrote it all out, there'd actually be 11 terms there, right? But our exponent would be 10. Which kind of makes sense, right? If we started at 0 here and we ended at 10, the numbers 0 to 10 would actually be 11. Okay, so that's how many terms we have. But then that means our exponent would actually be 10. So then this would just be 2 to the power of 10, which is equal to 1024. Next one. Okay, so this is the same thing, but you see it actually stops at 9. Well, okay, this actually isn't that bad either. So if you think about it here, we're just missing, like which one are we missing? Well, we're just missing plus 10C10. But what is 10C10? Well, 10C10, that's just 1, right? So why don't I do this? Why don't I actually just figure out what we had last time, right? The whole thing. And then we'll just subtract 1, right? So that would just really be 2 to the power of 10 minus 1, which is equal to 1023. All right, and we finally get to it, the binomial theorem. Okay, so all that hard work led to this. Now we're going to understand what we're doing here. So this is on your formula sheet, and we're saying in the expansion of, so just any binomial there to the power of something. Then we can follow this equation. And this equation's a little bit quirky. Well, and really just because of this part with the k involved in it. I'll explain how this is going to work in a second. But in this case, t is going to be the term position. So it could be like the first, second, third term. So like, you know, this is telling us what the value of the term is, right? So if I said like, you know, the third term, what that would mean, if I expand it out, you know, all of this equation is going to tell me this in the end. It's going to tell me what the third term was, right? So when I'm done with this, I should get some constant and then, you know, my variables on the end of it. Okay? So that's what this equation does. It lets us figure out what any individual term in the expansion is. Okay? So anyway, so that's what that's going to be. N is going to be the exponents on the original one. So that's just this, right? So whatever your power was. X is going to be the first part of the binomial, and y is going to be the second part of the binomial. Now, careful, because in this case, it's just that would be like my x would be a here, and my y would be b. But this would be like my x, and the -5 would be like my y, right? It's like both of them, because it's like plus negative if you want. Yeah, so I'll get into some examples of that, though. All right, so now we have this powerful tool. Now we can actually just use this to solve for anything we like. So what is the third term in the expansion of this? Okay, so I'm going to write down the equation again. So this would be t of, and I'll explain what this k is in a second. K plus 1 is equal to n c k x to the power of n minus k, and then y to the power of k. All right, it's not going to be as bad as you guys think when we get going here. So this k plus 1, right? The way I actually like doing this would be, we would put the actual term number there, right? So if I was looking for the third term, this is the way I do it. I'd say, okay, what is t of 3, right? I write it that way. So the third term. And then I just need to know what k is for the equation, right? Because you see that there's like a k in there and a k in there and a k in there. So they've written the equation as k plus 1. But then can you guys see, in order to make that true, then our k value would be equal to 2. All right, so it's going to be like 1 less than that one. So what I do is just right underneath it say, okay, k is equal to 2. And then I kind of have everything I need. But I know I like writing it this way because now I'm saying, okay, I'm looking for the third term. Okay? And then fill it in. So once I know that k is 2, then I'm just kind of plugging it in. I know everything else. So nck, so that's going to be, so our n value was our exponent, right? So that's going to be 5c2, right? Because that's our k value, times x to the power of n minus k. So that's going to be 5 minus 2. Okay? And then y is equal, and then y to the power of 2. Now, yeah, let's write it one more time. I just want you to see what's happening here. So in the end here, we're going to have t to the 3, or no, t of 3 is equal to 5c2, x to the power of 3, y to the power of 2. Now, why does this make sense? Well, let's look at this 5c2 for a second. Where have we seen that? Let's just think for a minute. We've got an exponent of 5, so that means that we have 6 terms, and we are in the 6th row. So I'm going to go back up and just show you what this looked like when we were in the 6th row. So the 6th row, when we were looking at this one, so 1, 2, 3, 4, 5, 6, so I'm in this row, and I'm on the 3rd term. Hey, look at that, 5c2, right? So that's all it is. This is just our coefficient out front in that term. So that's why that ended up being 5c2. And then our x to the 3, y to the 2. Well, that makes sense too, right? So if we're in our, let's go all the way back up to the beginning here. If we're in our 6th row, right? So this is like 1, 2, 3, 4, 5, 6. So we're in that row. We're in the 3rd term. Well, that's this, right? And do you remember how those, like x to the 3, y to the 2, they would always add up to our exponent? Okay, so I'm actually expecting that as a number now, aren't I? So now if you actually just put in 5c2 into your calculator, right, under math and then probability, then we'd say that the 3rd term would be 10 x to the 3, y to the 2. And there you go. All right, the 4th term of this one. Okay, so 4th term. Okay, so for this one, we're going to say, all right, so T4 is what I'm after, which would make K 3, right? So that's, I'm just taking care of that right now, right, in that equation. Okay, so now is equal to, and then NCK, so that's going to be 6C3 for this one, and then times x, but careful in this one, so our x value in this case is going to be 4b, right? Like that's our x, like this is our x term here, the whole, like both of them together, to the power of n, so 6 minus 3, and then times, and then our y value, but again our y value would be including the negative, so our y value here is going to be negative 5 to the power of 3. Now I know this looks confusing, but really in the end I've got numbers and I've got variables, right? So that's a number, and that's a number. So I'm expecting this is going to be some number to the power, or times b to the power of something, right? Once you simplify everything down. So if you simplify it all down, I'll do one more here. So I'll say is equal to 6c3. Actually, you know what? Let's just call that a number now. So you put that in, 6c3 is really 20 times, and then this is 4 to the power of really 3, right? So 4 to the power of 3 is 64, and then b to the power of 3. times, and then on the end of this, I've still got, well, negative 5 to the power of 3 is negative 125. Okay, and then really just multiplying all my numbers together out front, we end up getting negative 160,000 b to the power of 3. Okay, so that'd be it. Now, just notice a little one little hint here too, right? If you got a negative on the end, and we have an odd power, my answer should come out negative, right? Unless the front one was negative as well, but this will be quite often like just something that'll throw people off. They would have got this answer, but maybe they would have called it positive just because they put it in there wrong. But, okay. You know what? That example is pretty much the exact same. So just for the sake of time, you guys can try it for sure, but I'm just going to jump to the next one. Oh, sorry. It was not quite the same. This one wants the middle term, okay? So this won't be too bad. So the middle term, well, if we have exponent 8, how many terms do we have? We've got 9, right? You've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, well, what is the middle term for 9? Well, it's got to be 5, right? So really, the middle term was just, I had to do a little investigation into what term I'm actually looking for, but now I'm just set up the same way I was before. So I'm saying, okay, t of 5. So then k is 4. So then we could say, okay, that's going to be 8c4 times 3x to the power of, and then it was n minus 4, so 4. And then negative 2 to the power of, and then k, so 4. And then really I'm just kind of looking at all my numbers there mostly, right? Trying to figure out what my coefficient in the end is. So doing all that, we get 90,720. And then x to the 4, right? Because at some point I've got x to the 4 there. Okay, in the expansion of this one now, so this one now has a fraction, right? It says, which term in simplified form contains the variable a to the 4? Determine the coefficient of the term. All right, so again, this one, the only reason, it'll be the same thing, but the only reason why it can be a little bit tricky is because I need to figure out what is going to get me to a to the 4. So let's, just to get started, right? Let's write down some blanks so I can actually, maybe piece this together. Well, it's the power of 5, so there's got to be 6 terms. So I'm going to write down 6 blanks. All right. And I know following that pattern, right, that it was, when it was x plus y to the power of, let's say, 5. Do you remember how the left side started at x to the 5 and then marched itself down? So we've got the same thing with this one, but now it's going to be like a squared to the power of 5 is going to be our first one. And then a squared to the power of 4. And then a squared to the power of 3. And then a squared to the power of 2. And then a squared to the power of 1. And then finally a squared to the power of 0. So now, looking at the next part of this, right? If this was just our x plus y to the power of, let's say, 5. Do you remember how when we expanded that all out, that would be, well, the first term would be x to the 5, and then x to the 4, and then x to the 3, right? And it marches its way down. And the first one was like y to the 0, or just not even there, and then y to the 1, and then y to the 2, right? So like that was the pattern that we had going on there to begin with. So we're going to have the same thing here, but this is going to be like our y, okay? So what'll happen is our very first term on this end is going to be a to the power of 0, and then a to the power of 1, and then marching its way up. Just to make sense of that too, should be plus sign 0 too. To make sense of this too, let's rewrite the other way. This would be the same thing as having like our first term as a squared to the power of 5, right? That's like our x, right? That was like this. And then times, and then our y, right? That was like y to the 0. So that would be like, for this one, would be 1 over a to the power of 0. Do you see how that really just is the same as our first term? Right? Like the a just ends up on the bottom there, right? So hopefully that makes sense, right? So you're doing the same thing. So anyway, so you got a in the bottom, and then these a's are counting up. So a to the 2, a to the 3, a to the a to the 3. That was even worse. A to the 4, and then a to the 5. Okay, so now that I have that like generally set up, remember what we're trying to do here. We're just really trying to figure out which term we're trying to find, right? They just never told us which term, so we want the one though that simplifies down to a to the power of 4. So I think we can figure that out, right? This top one here would be a to the power of 2 to the power of 5. That's really a to the power of 10. And then a to the power of 10 over a to the power of 0 is just a to the power of 10. Well, let's go to the next one. So in the next one, we've got a to the power of 2 times 4 is 8 over a to the 1. Well, that would simplify down to a to the 7, so not a to the 4. Let's look at the next one. This next one seems promising. This would be a to the power of 2 times 3 is a to the power of 6. So that's a to the power of 6 over a to the power of 2. That would simplify down to a to the power of 4. So all of that work was really just to figure out that we're after the third term. Now that we know that, now we're going to use our equation, right? So t, 3, which would mean that my k value, 1 less than that, is 2, of, you know what, here I'll just write out the equation again here first. So then we have nck times x to the power of n minus k, y to the power of k. So let's just fill it in now. So t to the 3 is equal to, and then our n value here was 5, c2 times, and then let's just get straight in our minds what our x and y are. Our x is a squared, right? That's our x in this case. So we're going to have a squared to the power of n minus k. So 5 minus 2, so the 3. And then y to the power of k, so y to the power of 2. Sorry, let me back up there. I got ahead of myself with the y. Our y is not y. Our y would be this second part of the equation, right? So our y value would be negative 1 over a, and then that is to the power of k, right? So that'd be 2. All right. Now, just simplifying this all up, right? So now we've got 5c2 is really just 10 times a to the power of 6, right? 2 to the power of 3 is 6. And then careful on this one, because I've got a negative number squared, right? So that negative is going to end up making it positive in the end, right? So this can just become, times 1 over a squared. So then this makes sense, right? We were actually expecting this. In the end, this was 10 times, and then a to the power of 6 over a to the power of 2. This is a to the power of 4, or 10a to the 4. And that's that's good, because that's what they were asking us. Determine the coefficient on this term. So we found it, right? We know we did because we got a to the power of 4. So the coefficient is 10. All right, on to the next one. One term in the expansion of x plus a to the power of 7 is 84x to the 5. Determine the numerical value of a if a is greater than 0. Okay, now, it's kind of hard to see what we're even looking for here, but I'll tell you what, we pretty much want to figure out what term it is, right? And I think maybe we can make a bit more sense of it then. So let's do a little investigation here. So we know, so it's power of 7, so there are 8 terms. So we've got 1, 2, 3, 4, 5, 6, 7, 8 terms. And then let's use our little pattern here, right? I know for my x's, this is going to be x to the power of 7, right? And then, do you remember they walk their way down? Now the next one would be x to the power of 6, and then y, or x to the power of 5, and oh yeah, so that's it, right? That's the one we wanted. We figured that out from here. They told us also the coefficient, but to figure out what term it was, I was able to use that information. Okay, so now we know that we're looking for T3. All right, so if we've got, so T3, then I could say, well, K then is equal to 2. So now let's just go ahead and fill in what we know. So this is going to be NCK, so that's going to be 7C2 times X, right, because that's our first term there. X to the power of, and then it's N minus K, so 7 minus 2, so 5. And then for this part, we just know that it's A, so we'll say A to the power of, and then K, so that's 2. All right, so that doesn't really help us, right? We have that. We want to figure out what A is. Doesn't seem like I have enough information, right? Well, we actually do, because remember, this is the term, right? In the end, this thing is going to look like this thing. So I can actually say that this is equal to 84 x to the 5, right? They are the same thing. Now it's a bit more clear, right? We have an equation. This side is equal to this side. So now let's simplify this thing up a little bit. So one thing I can do right off the bat are x to the 5s. They nicely cancel. And then we end up with 7c2 is really 21. A squared is equal to 84. And then divide by 21. Divide by 21, so we get A squared is equal to 4. So then A is equal to 2. All right, find the constant term in the expansion of this. Okay, so this is really going to be the same skill as the one we did, actually 2 up, right? It'll be a similar question to this one, but we want the constant term. So let's kind of see what we're dealing with again. So we've got power of 8, so I'm expecting 9 terms. So 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. And then let's kind of get our bearings here. So we know the very first one is going to be, well, I'm going to just ignore the number out front for a second there, right? Because this first one's going to be, 2a to the power of 8. But I'm just trying to find my term number here. I don't really care about that 2, So I'm just going to say, okay, it's going to be a to the 8 for the first one, okay? And then on the bottom, this thing is going to be, it's going to have a to the 3 to the power of 0, right? That's how that was working in the one above. Okay, so then that's really just 1. That's not going to change anything, right? So here, let's just write a few of them out. So we've got a to the power of 7 over a to the power of 3 to the power of 1, right? These ones are going to count up. The top ones are going to count down. So then we've got a to the power of 6 over a to the power of 3 and 2. And then a to the power of 5. And then a to the power of 3. But you know what? Let's try some of these. Let's actually figure out what we're dealing with here. This one here, this is really a to the 8 over, well, anything to the power of 0 is just 1, so that's just 1. So that's not going to change anything. This one here was a to the power of 7 over a to the power of 3. That's not going to do it, right? I'd still have a to the power of 4. But what about this one? Now I've got a to the power of 6 over a to the power of 6. Those are going to cancel, right? That's going to be my constant term. It's going to be the one that when we go across this thing, my variables are going to cancel with each other. So that means I'm looking for my third term, right? So we are ready to start. So I'll say, okay, we're looking for T3, which would make K 2. And then, so this is going to be 8C2, right? It's going to be n, c, k, times, and then our x value here was 2a. So that's going to be 2a to the power of, and then it was 8 minus 2, so 6. And then times, and then the second part here is all of this. It's everything, right? So it's like the negative included. So negative 1 over a to the 3 to the power of, and then just k, so 2. All right, let's simplify this up a little bit. We've got, this is all equal to 8c2 is 28 times, and then 2 to the power of 6 is 64. And then a to the 6. And then this part would become, okay, again, just careful because now we've got an even power. And we have an even power with a negative number. This thing's coming out positive, right? So then this is going to just be 1 over a to the power of, and then 3 times 2, so 6. And then again, this is a good way to like double check that we did this right. We were expecting that those a's were going to cancel, weren't we? All right, that's what we found here. We already knew that from here. We knew they were going to cancel. This just kind of confirms it. So now the actual value here is just going to be multiplying our numbers together. So then when we're done, 28 times 64 ends up being 1,792. All right. Now, probably didn't think you were going to see these ones again. We've got the same pathway problems that we were doing in the other lessons too, right? So just to kind of remind us with permutations there, how we could solve this problem if we were going from A to B and we could only move to the right or up, then the way we would do that was we'd say, okay, well, how many paths are there? Well, there's 1, 2, 3, 4, 5, 6. Maybe I should draw it this way. There's like 6. And then there's 4 up. So in total, there's got to be 10, right? So we'd say there's 10 factorial over, and then the repeats, right? So the 6's all get they're all repeats, so that'd be 6 factorial and then 4 factorial. So if we do that, we end up getting 210. So 210 different paths through this thing. Now we can do the same thing using Pascal's triangle, actually, which is almost a little bit easier, more time consuming, but it's pretty simple. If I think, okay, how many paths are there from here to here? Well, there's only one. And then how many paths are there to here? Well, again, there's only one. There's just this one path from there to there, right? So there's only one. And maybe you'll see that there's one there as well. Okay? And then, yeah, 1 to that spot. You get the same thing happening this way, where there's one way to get there, one way to get there, one there, one there, one there, and one there. Now, why this is like Pascal's triangle is we're going to do the same little method here, right? That if there was one way to get here and one way to get here, how many ways are there to get here? Well, there's going to be this way, or there's going to be this way. So there's going to be 2. I'll just do this one more time explaining it, but how many ways are there to get to this spot? Well, there's going to be, this way, 1, 2, or 3. So that's going to be 3. You guys kind of see the pattern again here? That it's always going to be, I'm going to draw that in the same color, 3 and 2. Okay. It's always going to be this one and this one add together to give that one. Okay, so this one and 2, so 1 and 2 gives me 3. And now 3 and 3 add together to give me 6. And then we just kind of fill it in all the way, right? 1 and 3 is 4. 1 and 4 is 5. 4 and 6 is 10. And so on, right? So we'll keep going here. So this will be, 15. And then from, go on the bottom here again, 3 and 1 is 4. 6 and 4 is 10. 20. 35. So 5. 15. 35. 70. And then 6. and then 21, 56, 126, and then 7, and then 28, 89, oh 84 I mean, sorry, 84, and 210. So 210 ways of getting there. So same thing, right? So why this is kind of useful is it allows us to kind of do different shapes as well, right? Yeah, it's worth doing. Let's do this one too. So if we're going from A to B, so let's fill it out. So again, we've got one way to get there, 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 and there. And then 1, 1, 1, and 1. Okay, so that would make this 2, 3, 4, 5, and 3, 6, 10, 15, that'd be 4, 10, 20, 35, and then 5, 15, 35, and then we get 70. Okay, so now here's kind of the issue. So now we got 70, right? So now the question becomes, how many ways are there to get to here? Well, there's actually just 70 ways, right? If you think about it, there was 70 to get to this spot, and then there's still only 70 to get to this spot, right? Because that wasn't like another way, right? There was 70 to get to here, but then, you know, there was actually, that just kind of like carried on to this spot here. So there's still only 70. And it'd be the same on this side. And down even further, right? So then that would also be 70, 70, 70, and 70. You guys kind of see when you get to a junction point like this, it just kind of carries on with 70, or with whatever number you ended on. Okay, and then from there we can carry on like normal. So now this would be 140, and then 210. So then 210, 420, 280, 280, 700, 350, and then 1050. Okay, and we did do those as well, those type of problems using permutations, right? So we could have done that way, but this way is simple enough if you get good at that. All right, let's just do this one, last one. So A to B again. So if we're starting here, these are ones, right? Ones, ones. So let's kind of get going. So 1 and 1 is 2, 3, 3. This is 6. I'll kind of fill in what we know for sure here. This is 4. This is 5. And all right, yeah, we're starting to kind of run into some problems here, right? So the same as the last one, once we got to here, and this was 6, then there's actually only 6 to this side as well, right? So if we ended up doing all our different ways that we can get to here, it's not like there was more ways to get to there. It was the same thing. So it's still just 6. Okay, and then the same type of problem over here. So if it was 5 to there, it's still only 5 to there. And then that's kind of it. Then we have everything we need. So then this is 10, 16, that's 15, 31, 20, and then 51.